Hello, good time of day, everyone, and welcome to a new MLIR meeting. This week, Mahesh will present work done in the context of IREE, but that generalized probably further about code gen starting from MHLO using Linalg-on-tensors. Mahesh.
Thanks, Mehdi. Yeah, so today I'm going to talk about the work we started maybe a little more than 6 or 7 months ago, where we decided to move from MHLO being the front-end dialect to the compilation stack to Linalg-on-tensors. I go a bit into why we made the transition, and along the way, there were a lot of interesting abstraction challenges that we discovered, and just thought it might be useful to share. A lot of this was actually solved by Nicholas and Ben Vanek. And once those abstraction challenges were solved, me and the rest of the code gen folks involved in IREE kind of helped with moving the transition over. So it represents about 6 months of work across a lot of different people. Let me see. Okay, so I'm just going to start with just giving a quick overview of the IREE compilation flow as it exists today, just to kind of ground the discussion, and then go into the details of what are the representational challenges that we encountered while making the transition, and go fairly detailed into the IR, and so that it kind of makes clear what we wanted, what was the problem, and how we tried to address it. I don't think this needs to be like a formal presentation. I do have quite a bit of slides, but I'm happy to take questions in the middle. And if we don't get through all of it, I'm happy to pick it up in another meeting, because I don't think there's no reason that it should not be more interactive. That'll probably help the discussion. So starting with the current compilation flow in IREE, effectively IREE treats Linalg-on-tensors as the front-end dialect to the rest of the IREE compilation stack. And within the IREE code base right now, there are separate pipelines that convert what you could think of an actual input dialect like an MHLO or TOSA to Linalg-on-tensors. So these are not in the core IREE compilation stack, but they're outside of IREE. And the MHLO to Linalg-on-tensors conversion lives in the MHLO repository. The TOSA to Linalg conversion lives in the MLIR repository where the TOSA dialect is. Once we enter the Linalg-on-tensors is where you start doing things that are more part of the IREE compilation stack. So the first thing we do is we do element-wise fusion of the operations, so that you reduce the number of operations with Linalg-on-tensors. So if you do a naive conversion from one of these dialects, you'll end up with a lot of operations, and you want to reduce the number of operations you have, and element-wise fusion helps you do that. So after this stage, roughly one Linalg-on-tensor operation corresponds to one dispatch region. So IREE has a host device model where you take your input model, you then partition it into several units of execution, which are captured by the dispatch work groups. I'll go into a little bit more detail of what these are later on. And the dependence, there is what is within a dispatch region gets compiled down to the executable code that is run on the device. On the host side, the dependence between the dispatch work groups is tracked, and then there is scheduling and buffer allocation for satisfying dependencies between the dispatch regions. So once you do the element-wise fusion, roughly one operation on Linalg becomes one dispatch work group. You can further reduce it by doing tile and fuse, where you could try to fuse, say, a matrix multiply with its consumer, if it's like a bias-add or something like that. That's only worked. It works in fail. We haven't really pushed on it, but it does work in practice, and there are some cases where we do use it. The other thing that we do at this stage, we actually distribute the work. So a dispatch, what is represented in a dispatch work group is effectively so the flow dispatch work group is already partitioning the work along a 3D grid of process XYZ. If you're familiar with the CUDA or SPIRI execution model, it effectively does the same thing. So what you get is the work to be executed by one processor element in this 3D grid of process. So all of this is done during the dispatch agent formation itself. So it's actually distributed at this stage.
Mahesh, there was just
Yeah.
a question on the chat. Someone was asking, how would you model or handle or represent a fusion of two convolution?
So it depends on how you would. So right now, we don't do fusion of two convolutions, but if you would do, then you can think of it in the context of Linalg. If you have two convolutions, okay, so this is a little bit of detour, and I think related to one of the discourse first. So the two fusions are, the element-wise fusion takes two Linalg operations which represent perfectly nested loops, and it generates a new operation which is a perfectly nested loops. And the tile and fuse is another way of doing fusion where you take two operations and you create an imperfectly nested loop nest. The tile and fuse kind of represents that. And as I go further on, I have explicit examples to represent that. And convolution fusion would basically require you to have imperfectly nested loop nests because you have reduction dimensions. So you have to complete all of the reductions of one convolution before the result is ready for the next convolution. So you have imperfectly nested loops. And you would represent fusion of convolution using tile and fuse. And that is kind of orthogonal to IREE. It kind of comes naturally if you have a transformation that can fuse two convolutions in Linalg, then that automatically will be reflected in the way the dispatch regions are created.
Thanks. Another question, which is, can you and do you want to target multi-core, multi-processors, and/or multi-GPUs?
So this already targets multi-core. So at this stage of the creation, there's nothing specific to GPU or your target hardware. All the backends that IREE supports take this as the input. So on the CPU, you would think of the 3D grid of process as a virtual process. They get mapped to physical threads. The mapping is up to the actual scheduler, and that's how you would target multi-core that's how we do target multi-core in IREE. Multi-processor, if you're talking about like a distributed memory system, that is not what this does because it's still a shared memory system. If you look at the inputs to the dispatch and the outputs, they are the entire tensor. Each dispatch might just create a part of the tensor, but at the end of the computation, when you do the bufferization and these get mapped to actual physical memory, each dispatch will probably be computing only a portion of the output. So doing distributed memory is not something that we've looked at right now. Maybe in the future, that's something probably Ben could expand on later in a different ODM if that is of interest.
Thank you.
Okay, so going ahead, so I talked a bit about this. So the region within the dispatch workgroups gets converted to a HAL executable. HAL executable is basically, think of it as a unit of compilation if you're doing like an object file. And this is what finally is executed on the device. So in this case, it's say you have a Vulkan executable. You could have multiple targets, and you would compile the module within the executable for each of those targets. So here, if you have a Vulkan, you would take the module that you see in the HAL executable and compile it down to SPIRV code. So that is what happens within a dispatch workgroup. The code outside of the dispatch workgroup goes through interkernel bufferization, stream formation, basically scheduling, and gets converted to a host side virtual machine code. So that, along with the serialized executable for each HAL executable, are then put into an IREE flat buffer. And what the runtime does is it basically takes this flat buffer. It has a tiny VM which knows how to interpret the host side VM code that was generated compilation time. And as it's executing the VM instructions, it's launching work on the device, which is like how you would launch a CUDA kernel, for example. So this is, if you're familiar with the Vulkan programming models and CUDA programming model, this is effectively emulating it, but it works across different backends because the HAL abstraction, which is the HAL layer, which is a hardware abstraction layer, has the same idea behind it. Within a HAL executable, there is intra-kernel bufferization, things you would want to do within a kernel, like vectorization and memory promotion if you're targeting GPUs. And there's a difference between the inter-kernel bufferization and intra-kernel bufferization. They're targeting two slightly different things, and I'll go into what they are later on in the talk. Okay, so that's a brief overview of how the IREE compilation flow looks. So when in IREE, before we started this transition, we used MHLO as the front-end dialect to the compilation stack. And the first thing that you would do is we had a set of rules that would look at the input program in MHLO dialect and figure out which operations can be grouped within a dispatch region. Loosely, these rules were which operations can be fused by the backend. So it would say if you have an add, if you have a broadcast followed by add, the backend can probably fuse it into a single kernel, and you would put that into a dispatch region. If your backend couldn't fuse the dot with the broadcast add, it would put that in a different dispatch region. And then once you create the dispatch region based on this set of rules, within each dispatch region, you would do the conversion to Linalg, do element-wise fusion, you would do tile and fuse, and distribute within a dispatch region, and then generate the executable for each dispatch. This turned out to be suboptimal because you always have this oracle which is trying to guess what the backends can do, and because it's a heuristic of rules, you would always end up in cases where you would have suboptimal dispatch region creation. For example, you would have cases where a broadcast, instead of being fused with all its users, you would materialize the broadcast explicitly in memory, which is almost always not a good idea. And there's a GitHub issue that was filed on IREE that goes into more detail of what that is, and it's linked over here. The other issue that you would have is the IREE setup, the way things go, it is better to have one dispatch region lower to one kernel. Think of it for GPU, but it makes sense for CPU compilation as well. It is useful to have all the memory needed for the dispatch being explicit arguments to the dispatch region, and within a dispatch region, you have only one kernel. This gives the host side complete control over bufferization and how it wants to reuse memory and how it wants to schedule the work, and can make better decisions in terms of scheduling and allocation than if a dispatch region itself has to split the work, has to manage intermediate buffers, and has to do some kind of scheduling between kernels within a dispatch region, which it would have to use a pessimization, a barrier which would be a pessimization in terms of execution. So all of this led us to kind of have this fairly strong requirement that we want to have one dispatch region mapped to a single kernel, or a single loop nest that you would execute on the CPU. And if you have operations like MHLO pad, that would be hard to satisfy. A pad, when you go from tensors and you convert to memory, effectively is a fill, where you fill the pad value on the entire input, and then take a subview of the region that needs to be, a subview that corresponds to the input, and do a copy. So if you look at the amount of work that each of these operations are representing, the fill has higher parallelism than the copy. So generating a single kernel to handle this is complicated, and almost always will involve some amount of pessimization of the amount of parallelism that is exposed. So this is a simple case, but this is representative of the kind of things that you would run into. And there was no way, if you're starting with MHLO, to have a way in which you could satisfy one dispatch region mapping to one kernel in such cases. So this was another reason why we moved to use Linalg-on-tensors, and it'll become clear how that works out. There's a question on chat about interkernel bufferization. Is interkernel bufferization the phase that optimizes for memory placement of intermediates between kernels? No. Yeah, sorry, I misread it. It is interkernel bufferization that is optimizing for memory placement between kernels. So the memory placement is a little bit overloaded. In IREE, current IREE compilation stack, we are not targeting multiple architectures. So if you're targeting CPU, then you want all the memory that you're using to live on the device, which is the CPU. If you're doing GPU, you want to have all the memory for the interkernel dependency to live on the device. So the optimization to make sure that you're reusing buffers from intermediates is done on interkernel bufferization. But if the question was asking about memory placement in terms of whether you place on the device or the host, that is not a concern right now, because all the memory is always on the device. Okay, so all this boiled down to like a phase ordering issue. Effectively, at the MHLO level, if you want to create dispatch regions, you would have to guesstimate what the backend has to do and have a patchwork of rules that kind of matches what the backend does. And as you modify the backend to potentially allow more fusion, you would have to go back and reevaluate the rules, and it would be hard to maintain a consistent set of rules that would do what you would expect. And in general, you could also have something that would be different for each backend, though we do discourage from doing that. It was getting to a stage where this was not manageable anymore, so we needed a different solution. So I just going to walk through an example of how this looks in Linalg-on-tensors approach and how this is sort of mitigated. So let's start with the broadcast add example that I showed earlier. In MHLO, when you lower it to Linalg, it becomes a MAC-meld, generic op to do the broadcast, and a generic op to do the element-wise add. When you do element-wise fusion on it, the broadcast gets folded into the point-wise add by you basically just pull in the operand and you change the indexing map used. That's the fusion of the broadcast with the add, and then you have the MAC-melt and the generic op, which you can then tile and fuse. Just a note on distribution. When we do tile and fuse, you also do the distribution of the tiles that are fused. So here we use block cyclic distribution, and so you use the ID, the number of process, and the size to create a loop that does the cyclic distribution of the tiles that you create. And because the tiles are itself doing a block of the computation, it models block cyclic distribution. And putting all of that together, you get this loop nest where each dispatch region is doing a certain tiles of the computation distributed in a block cyclic way. It is going to compute a tile of the MAC-meld using whatever inputs it needs based on the indexing patterns of the operation. Once you create a tile of the MAC-meld, that is used to compute the tile of the bias add computation result, and the result is just written out, is the result of the dispatch workload. And this is effectively how, because of this, there is no place where using this approach, there is no place where you actually had any heuristics. Since you're computing this, the way the dispatch region is created is by construction, already modeling what a work group is doing. You don't need to have any rules or heuristics to model, can a backend fuse it, or can it generate a single kernel or not. By construction, it is already modeled in a way a backend can lower it to a single kernel. Okay, so that kind of is the first part of the talk. So as we move to Linalg-on-tensors, there were a few representational challenges that need to be addressed, and these are the three things that I'm going to talk about here. One is, and this will become more clear as we go along. So the first thing that we had to adapt is the Remodify write semantics of Linalg operations. So I'm going to take a detour here and explain what that actually means. So before Linalg supported tensor operands, it was initially designed to work on memrefs. So MAC-meld would take, Linalg MAC-meld would take two memref operands for the LHS and RHS and one result operand, and it represented a read, modify, write semantics. So in loop form, you would have the M, N, and K loop. You would read the LHS, RHS values, do the multiply, and then the add would read the value of the result, perform the add for that particular iteration point, and then store the result back. This is not how you would finally generate the code, but this is how it is represented. So this represents in what you would expect from BLAST, where you do a C plus equal to A times B instead of doing C equal to A times B. And that was the semantics of Linalg operations. So Linalg matmuld is what is known as a named op. All named ops in Linalg and implement an interface which is known as structured op interface, and they effectively are a specification of what a Linalg generic allows you to represent. So it's a fixed representation of a Linalg generic operation. So let me go into details and probably it'll become more clear. So if you try to represent a matmuld using a Linalg generic, then you would basically specify the iterator types as having iterator types, which is the number of loops the operation represents. In this case, there are 3 loops, parallel reduction for m, n, and k loops. And then this represents the loop nest that the operation is specifying. You would use the indexing map to represent, for a given point in the iteration space, what is the point of the data that you're reading. So the first one represents the mapping to the first operand, which is the LHS. So for an mn k point, you would read, for an ij k point, you would read I and k. The second one represents RHS, so you would read k and j. And the last one is the output, which would read I and j point. So that represents the iteration space and the data access. The computation within each point in the iteration space is represented by the region of the generic op. So here the number of arguments to the block is the number of inputs plus the number of outputs. And you would represent the computation as, so the first 2 correspond to the input, the third corresponds to the output. You read the 2 inputs, do the multiply, you read the output, and then you yield. The yield is implicitly representing a store to the result. So this implicitly represents the same computation, the loop form I showed in the previous slide. And what named ops is effectively doing is a fixed representation of the iterator types, indexing map, and the region for a given operation. Another aspect of structured ops is that the loop bounds are completely determined based on the shape of the operands. So in the matrix multiply example, given that you're accessing the LHS using an affine map, which goes from D0, D1, D2 to D0, D2, which represents IJK to IK, and you know the shape of the LHS operation, you do an inversion to say that the outer loop has a bound which is same as the first dimension of the LHS, and the inner loop has the bound which is same as the second dimension of the LHS. You do the same thing for all the operands. So if you take the RHS, you get representative of the inner loop of the inner loop. You get the bound for the inner loop as the first dimension of the RHS, which by a matrix multiply property has to match. This is treated as it's treated as an assertion when you lower into Linalg. So if you lower into a Linalg matmuld operation, it is assumed that the second dimension of the LHS is same as the first dimension of the RHS. That's the semantics of the operation. And you get, using the second dimension of the RHS, you get the bounds for the end loop. So now you have the bounds of all the loops. And going further, if you look at the affine map for the output, you again get the bounds that you get if you use the output should match the bounds that you've already computed. So it is assumed that the indexing maps and the operand shapes already satisfy the bounds property that there's consistent. There's no inconsistency here. So Linalg itself doesn't check that. It is assumed to be the property of the output. So another thing to notice is that if you take an element-wise operation which has only parallel semantics, you actually don't need to do a read, modify, write semantics. I'm just placing this in context. It will become clear why this is important to keep track of. There's no read, modify, write semantics here because when you're doing a completely parallel operation, you don't you're always just updating the output. You're just writing to it. You're not reading from it. There's no reduction happening. So in this case, the way that manifests in a Linalg operation is that the argument of the region that corresponds to the result in the basic block is never accessed within the basic block. So this is an indication to say that this is actually not a read, modify, write semantics of, but it's just writing to the output. And that is because the operation is representing a parallel computation. Yeah, sorry, memref.dim, you're right. I'm still not fully internalized the split of the dim operation. So if you had a memref operand, you should use memref.dim. So I'll fix the slides later on. Thanks, Alex. So how do you represent read, modify, write semantics in SSA value? When you move to tensors, all elements of the tensors are defined simultaneously. So there is no opportunity to do an in-place update of the operation. So something like a matrix multiply, which is representing plus equal to a times b, you cannot do that in tensors because you cannot read and modify the value of the tensor in place. So there's two solutions that you can do. The first one is, instead of representing a plus equal to in the operation, you just say that the result is c equal to a times b. So there's no initial value. In that case, you don't need a read, modify, write semantics, but you also lose the ability of having initialization to your initialization value to the output buffer. The bigger problem is that there's actually a fundamentally different computation in tensors than what you have in buffer representation. And then you have to somehow resolve this difference when you convert from tensor representation to memref representation during your compilation. The other option that was finally taken was you, instead of having two operands, and so you in the tensor world, you still keep three operands and you have a result. So you have an LHS and RHS value, which is the input. You have an outs list, which is the initial value of the output for the matrix multiply operation. And the result is then going to be init plus LHS times RHS. There is also an implicit requirement that the shape of the init is same as the shape of the result. And when you convert this to memrefs, you would basically collapse those two tensors to point to the same region of memory, and then you get the read, modify, write semantics for that. So this is called tied operations. There's no real interface that manages this right now in core, but effectively the result and the init tensor are tied to say that they will map to the same buffer when you convert it to memrefs. So this solves the read, modify, write semantics problem. So now going back to the case where everything was parallel, where you don't have read, modify, write semantics, you don't need an explicit initial value. You could just have a list of input tensors, and you don't have to change the semantics at all. But if you look at the case where you have a broadcast, for example, so this example here is a generic op which represents a broadcast. It's just simple broadcast where you're broadcasting along the second dimension. If you want to compute the loop bounds of this operation, the loop bound is only obtained from the result of the operation. Nothing in the operands gives you the loop bound of the inner loop. So this becomes a representational issue because the op itself does not have all the information that it needs to completely specify the result in a way, because until you get the result, you don't know what the bounds of the loop is. So this causes some strange behavior when you try to lower it to loops, because you need the result to get the loop bounds, but you don't have the result. And there are ways to resolve it. One way to resolve it is that you have a side channel where you capture the shape information of the result through another dialect or another sequence of operations, so that you can query the IR to get the shape of the result when you're going into loops. The other solution that we went with was you have a dummy initial value, which is only there to carry the shape information. So you create a tensor whose shape is the shape of the output, and then you make that an explicit operand to the generic op. In this case, you don't actually need the value of the output because you're going to completely, the initial value doesn't, what value the init has here when you start with doesn't matter. The generic op is going to overwrite it, but you only need it for the shape. And with this, each operation has all the information it needs to compute the result. So I don't know if this was intended, but at the time when later on, it became very clear when we were trying to look at dynamic shape code generation, this representation is really powerful. To some, so this representation is really powerful, and you can do code generation for dynamic shapes for the most part without any external shape information, because the operation itself is carrying all the shape information. This is something that we've started to push on and kind of prove out in IREE recently, and so far it's been working out fairly well. I haven't had a case where that we had to rely on a side channel of information for the shapes. So there's a question on chat saying that is it like LLVM undef? I don't know. You can think of it that way. It's really meant to capture the shape. So it's an operation to say I need the shape of the output, and it's not really looking at the value. So there's no, the LLVM undef, from what I know, has some connotations associated with how compiler optimization deal with undef. Kind of is not relevant at this point because we never actually look at the value, and there's no semantics of what an optimization can or cannot do with it. It's just a way to represent the shape of the result. I don't know if that helped, but that's kind of how I see it right now.
Mahesh, you said earlier that the out parameter is used for the initial value, for instance, in a matmul, but now you're saying that you feed it a value that is just the shape, or that you're only going to use the shape.
That's right. So for matmul, for the operations, so all Linalg operations can represent a Linalg generic. So for a Linalg generic operation, which has a reduction iterator type, then the value becomes important, because then if you have a reduction iterator type, you're doing a read modify, right? In the cases where you don't have a reduction iterator type, you don't need the value. The value is never actually used, and you would only actually need the shape. That's the distinction. But in terms of representation, it unifies the representation. You don't need to have an out list only when there is a reduction iterator type. You always have an out list where the number of elements of the out list is same as the result, and the shapes have to match. And whether you use it or not becomes a property of the operation itself.
Okay, and so what happens if you have a reduction, but you use the init tensor?
That would be wrong. You should not do that. There's no way. I think it's not verified right now, but yeah, you should not do that.
So I'm going to read out loud for the recording. Alexander says that having a fake init tensor composes well with the tiling of Linalg generic. If we tile Linalg generic and then the new tiled output is actually a slice of the original init tensor.
Yeah, that is actually, yeah, that's a good point. I think the previous, when I used the slides in a different context, Nicholas brought this up too. It is a little bit involved to understand without understanding how Linalg tiling works. But what Alex is saying is right, because when you do tiling, you are in TensorLand, you need to compute a tile of the result, and you need a place to put it into. So it'll become clear as I go through the slides. What Alex
that makes sense. I think what Alex is saying is that if we were representing the shape separately for those, then during tiling, we would also need to specifically compute the shape of the tile. While here the shape is implicit as we tile a tensor, even though we never use this tensor, we'll have the shape available as well. And so we tile only uniformly whether we use the value or not. And we have the shape as a side effect of this.
Exactly.
Which simplifies
it does simplify tiling implementation quite a bit, yes.
Also, it can be some other tensor that has the same shape and is already initialized with Linalg view or something.
Yeah. So if you're tiling a matmul, then the input, if you were tiling a matmul, then the value you get in the out list is actually the result of the fill. So that works out when you tile on tensors. Maybe we can come back to this when we go a little bit more detail into tiling of how tiling works on tensors. I have a lot of IR related to that later on. That is used later, collate outputs and output. Actually, if I understand, so there's a question on chat. Saying that linear generic on reductions has a very particular form that is used later by bufferization to collate outs and outputs. Actually, I'm saying that all linear operations have that. There is an explicit understanding that the number of elements in the outs list is same as the number of results, and all of those will basically collapse to the same buffer when you bufferize. So it uniforms the behavior irrespective of whether you have reduction or you don't have reduction. Okay, so going into tiling, now that we're talking about tiling, I'll go a little bit of detour on how tiling works when you're using on memref. So tiling is one of the core transformations in Linalg. Like tile plus fuse is effectively you tile the consumer, you compute the operands of the tile you need, and you compute the operands of the tile in place. So that gives you tile and fuse. And the linear tiling algorithm uses the indexing map to generate the tile implementation of an operation. So any operation that implements the linear structure of interface, which specifies the indexing maps and the iterator types. So I don't think the iterator types actually matter. That use the indexing maps, the tiling algorithm can tile that operation, and by construction tile and fuse that operation with other linear operations that implement the same interface. Tiling is parametric, so this is how the tiling code looks like when you do it on memref operands. You have loops that go over the tiles, so the M and K inter-tile loops. You take a sub view, which is okay. This slide is dated. I should really update it to say tensor extract slice, where you take a slice of the LHS required to compute the tile of the output that you want. Do the same thing for the RHS. You then, because you're in memref and you're doing Remodify, right? You take a tile of the output, and then you do the mat mult. And this gives you, each mat mult here is just computing a tile of the final result. When you are on memrefs, you can also represent the parallelism in the inter-tile loops using SCF parallel operation, where you say that the M and N inter-tile loops are parallel, and you could use this information later on if you want to distribute these loops to different workers. The next detour is a little bit about how loop structure control flow works on tensors. So on tensors, you can think of each iteration of the loop as being a function with arguments being the induction variable and the values that represent the loop carry dependence. So each iteration is computing the value that needs to be yielded to the next iteration, and then the next iteration is going to take that value as an argument and compute it and yield the value for the iteration. It keeps going on. So in SCF4, that is represented by an argument list, where arg1 represents the loop carry, the value which is the loop carry dependence. It gets an initial value, which is the value at the 0th iteration, and the value that is yielded within one iteration becomes the value of arg1 in the next iteration. So that's the semantics of loops on tensors. And if you put that all together for tiling in Linalg-on-tensors, you would have the tile loops, basically get the init tensor that Alex was talking about as the operand to the outermost tile loop, the argument that represents the loop carry dependence then gets passed through the loop nest, and then within the body of this, you would extract the slice that you want for do the tile computation, and then you need to insert this tile back into the arg value that you get for the innermost loop, and then return the whole tensor. this is the only way you can make sure that the final result that you get has the contributions from each of the tile loops. So within the loop body, you compute a tile of the result. You take the current value of the tensor, you insert the tile into that tensor, create a whole new tensor, and then you send that, you yield that tensor value, which goes to the next iteration, which computes the tile of that tile for the next iteration. So this requires the use of an extract slice and insert slice. I did update these slides apparently. And this insert slice is known as a destructive update because you are creating a whole new tensor at every iteration of the inner loop, and you need to yield it. This is the only way you could represent semantically the tiling of Linalg-on-tensor. Tiling in the context of Linalg operations when they have tensor operands. So this is a little bit involved. If there's some details that I'm missing, I can go into more details of it. But in a nutshell, it's basically you have to compute an entire new tensor for every iteration of the tile loop. So the side effect of this is that you lose the information that the intertile loops can be parallel, because every iteration now there is an explicit dependence between every iteration of the loop across the loop nest. So if you were doing tile and distribute using memref, using SCF parallel, or using the semantics of parallelism of the intertile loops, that doesn't work anymore when you go when you move to Linalg-on-tensors, because each iteration now has an explicit dependence. This is essentially an abstraction gap. There's nothing fundamental in the computation that has that dependence. It is a representation tensor that is introducing this dependence. And if you, in your compilation flow, when you go from the tensor to the memref representation, you can get back that parallelism. But if you lost the representation that the loop itself is parallel, that will be very hard to recover. So in general, it's just an abstraction gap, and it's a fake dependence that was introduced by the representation, and it's not fundamental to the computation itself. The issue is really the destructive update, because each tile has to compute its tile, insert it into the result of the previous iteration, return a whole new tensor. That is what creates the dependence. So it's the destructive update that is adding the dependence between different iterations. The tiling happens sequentially. It seems like a good motivation, tensor of tensors or something like that. Not sure I follow that question. Stephen, if you can throw a little bit more light on what you mean.
So basically, when you have like a matrix multiply, you can treat each tile as a matrix.
Yeah.
Which is kind of the point of the whole C equals A plus C plus equals A times B, right? Yeah. And so what you'd really like to do is to have a Linalg generic matmul that operates on tensors. That it operates on tensors of tensors, so that each inner loop, instead of being a slice update where you're enforcing this sequential operation, is expressed as a Linalg operation.
There's still an issue of how do you make sure that you don't lose the update from a particular iteration, because whatever even if it's a tensor of tensors, even if you're updating one of the inner tensors, because you have to yield the entire value, it's an SSA value, you have to yield the entire value, you have to still do a destructive update.
Right, but it seems like it's the problem is because you've represented the outer loops by SCF4s. Whereas if you represented the outer loops as something else, for instance, the outer loops could be a Linalg generic operation.
I think you're going to the solution that we came up with.
Okay, great. Maybe I'm jumping the gun, but go ahead.
Yeah, so this is right. I think eventually we landed on something similar to what Stephen was describing. Initially, we tried to do this and try to see if there's a solution here in IREE itself. So going back trying to kind of get what are the semantics that we need to support before we can get to a representation that makes sense and generalizes more than IREE, and that has happened now and it's in core. So when we started this, we went back and looked at the dispatch region formation. IREE does a tile distribute during the dispatch region formation. So one of the ideas that was put forth was, within a dispatch region, we can have two operations, one which loads a tile of the tensor and the other that stores a tile of the tensor. And the actual load and store is not explicitly represented in the IR, but is implicitly handled behind the scenes. So in the IR representation, you have a mechanism to say, give me a tile of the tensor. And you have another instruction that says, here's the tile I want to write back into the result. And you would say there's some underlying mechanism that basically does this for you. Then it comes to a question of, if you're doing distribution, how do you synchronize between these different loads and stores? And we went with the assumption that if there are multiple loads and stores that are going to be writing to the same region, reading or writing from the same region, then that's a race condition. So you should not be doing that. And fundamentally, large tiling doesn't do that. So that was one of the things that we started with. So in IREE, so this is a solution that we have in IREE. This is not what is there in core right now, but it is based on this. The dispatch work groups, going to a little bit more detail, you can think of it as having 4 operands. The work group has a region which represents the computation within the region, and it has 4 operands that represent the ABI. So there are 3 inputs and 1 output, represented as 3 flow tensors and 1 flow tensor with write only. Though it's called a tensor, it's really a representation of the ABI. So you can load from these map to the LHS, RHS init values. That's the first 3 arguments, and R3 maps to the result. So that captures the ABI of the dispatch region. And within the dispatch region, you can use the flow tensor load to load from one of the inputs or outputs, load from one of the inputs and use the flow tensor to write to one of the outputs. So you assume that there is an underlying mechanism that gives you this. So you then don't need to use the destructor update. You don't need to use a way in which you have to thread through the value computed by one iteration of the intertile loop to the next iteration, because you're kind of abstracting that out and removing the destructive update. So this kind of solves the abstraction gap. But in theory, the runtime actually doesn't need to do anything. When you do convert it to memrefs, in IREE, the ABI gets translated to a binding with explicit read-write access specifiers. So the 3 arguments, which were flow, tensor, read only, became read binding, buffers with read only accessor types, and the last binding, which was a write only, became a buffer with a write only accessor types. And because you have the information that a flow tensor load is reading from the ABI, boundary, you can convert it to a subview and recover the same behavior you would expect if you had if you did this in memrefs to start with. So that kind of helped bridge the abstraction gap, because of introduced by if you just did tiling using Linalg-on-tensors and SCFRs. A version of this is now upstream using the Linalg tiled op. I'm not going into details of this here, but it's effectively kind of modeling the same kind of behavior. And I think Alex just sent out an RFC, which kind of gets it closer to what this does. Yeah, that's exactly it. That's something that we are looking at. Alex is saying on chat that it doesn't have to be a slice. We could have something that gathers or some other subset. If you're looking at sparse computation, you could do any way of getting what you want for the region that you want to compute in. And that's kind of some of the things that I think a bunch of folks are looking at. All of them are looking at the same thing because we seem to have the same problem. The last thing that I wanted to get to, I don't know how much time I left. I have like a few minutes. Is that because there are explicit accessors of read and write only, and the Linalg operation has in it a result value. When you convert it to memrefs, you actually need to introduce an explicit copy, which takes the value from a tile of the initialization, initializes the result tile with the initial value, and then does the matmod, does the read modify, right? So again, because of the way things are represented in tensors and memrefs, we have to do this copy for correctness. And you don't want to do this copy in general. And the way we address this in IREE, and I'm not sure that there is something that exists in code at this point, is that we added a read-write accessor type at the flow level, which said that, okay, this is something that allows you can both load from it and store from it with the same semantics. If you're loading and storing to the same tile, then that's a race. And with this information, you can then basically eliminate the copy, and your accessor for the final, when you get to HAL layer, has a read-write accessor. And then that allows you to do the modify update in place, and you don't need the copy. So this is my last slide. I wanted to briefly mention topic of bufferization, which is a very complex topic, which probably needs an ODM by itself. And there's a lot of work that has happened in core. Nicholas has added a whole bunch of stuff to do bufferization in the context of Linalg and to avoid doing extra copies and trying to doing it in place. In IREE, the way bufferization looked at is that there really two bufferizations. There's an inter-dispatch bufferization that happens outside of the dispatch regions that satisfies the dependence between the dispatch regions. And there's an intra-dispatch bufferization that is tasked with taking the buffers that you're getting through the ABI, making sure that all the computation is happening in place without additional heap allocations. And this is where the read-write annotations help. So I'm not going to go into more details here because this is a fairly involved topic and something that probably requires its own discussion. So that's my last slide. So if there are any more, yeah, that's my last slide. If there are any more questions, you can take questions.
Thanks, Mahesh. We indeed have just a few minutes for questions. So
I did get through all slides. I didn't expect to get through all slides. Okay.
Feel free to unmute yourself if you have questions. Good. Go ahead, Alex.
Mahesh, like this read and write annotations that you showed in the previous slide. Can you go back there? Yeah. I don't know. Next slide.
Okay.
Yeah, this one. Read write. How is it populated? Is it populated when you tile, or is it a result of some analysis? Or?
So it's done here. So when you create the tile, yeah, you're right. So it's done at the flow level when you're creating the dispatch regions. You can basically look at the operations and you look at the recomputation within a dispatch region and say that I can try to do this in place. In theory, we need an interface here. There's probably a missing interface upstream. There is a version of this interface in IREE, which maybe we should try to upstream some at a point in time, where for every operation you can know, can this operation be, when you convert to memrefs, can the two operands, the result reuse the buffer for one of the operands? This is an interface that you can define for each operation. You can use that to kind of look at the computation within your dispatch region and say, okay, this is the ABI I would want. So this is actually flipping the way this works. When you create the dispatch region, you're telling the ABI that I can do the compilation using read, modify, write for the result by reusing one of the buffers for the input. The inter-kernel bufferization then uses this information when it does the bufferization, and then it satisfies. It gives you what you want. You say that I can do this in read write, and then the inter-kernel bufferization takes care of that.
Yeah, does it currently work for matmul only, or it works for all types of Linalg generic ops?
So it works on all Linalg generic ops. If works on non-Linalg ops as well. For example, if you're doing subtensor insert, the destination and the result of the subtensor insert. Sorry, I should use a new term. Extract slice. No, it's insert slice. Insert slice, the destination and the result can basically reuse the same buffer if certain properties made. So you could do that even for that. So it's a generic interface that is not related to just Linalg. You could do it for many other operations.
So currently in comprehensive bufferization that Nicola submitted, it's all kind of, this code is duplicated there, like, because all the reads and writes, they are annotated right there.
Yeah.
Okay. Yeah. Thanks.
We have a question on the chat. I'm just going to read it out loud. Do you manage to bypass libraries like BLAS completely? And what is the penalty of that? And the second, yeah, go ahead with this first question.
Yeah, so we don't only target x86 in IREE. IREE targets ARM, Vulkan, CUDA, and none of these places we have actually tried to use BLAS. That's always been the fallback if you really need to. One of the core things that we want to push out in IREE and really push on is using completely cogent strategies, completely cogent-based solutions for operations like math-multi combination. The cost, let me say on ARM, it's not, I think we have enough of the pieces to get to similar performance. I wouldn't say that we've actually implemented or plumbed through all of these. There might be pieces where it doesn't, but I think we have all the required technology to kind of get the same performance that you would get from a library, and also do things like fusion that you can't do if you're using a library. So that's the core goal of what we want to do in code generation within IREE and even outside of IREE. That's one of the goals for Linalg in general. And a lot of it.
Question. Yeah, let me just read it out loud so that it's on the recording. Is the top level single-threaded, meaning that a single thread that dispatches towards the various cores, or is the output multi-threaded?
Is the top level single? Yeah, I think the dispatch is single-threaded, but it's actually, yeah, I don't. It's like a command buffer. If you're familiar with how Vulkan works, you are submitting a bunch of work to the device to do, and there's an explicit synchronization between different command buffers. So it is an asynchronous execution, and all the asynchronicity is managed by the device. So the recording of the work itself is sequential, but the work itself can be done in an asynchronous manner. Is the output multi-threaded? Each dispatch region is doing things on a CPU, can do it in a multi-threaded way. But like I said, because the recording of the work itself is single-threaded, I don't see much benefit in that being multi-threaded, because the work is just represented as asynchronous task that needs to be executed, and the asynchronicity can be used by the device in whatever way it can.
All right. Any more questions? Maybe I have one last half question, half comments, because I think some of the things became also more clear. You talked a lot about destructive updates and things like that. There is a lot of coupling or weird interaction between the bufferization and the tensor world. And I think Linalg was originally started with memref, and that's why we have all those outs as well, because that was the form to write. And when tensor was added, we kept the out for the initial value, because like it reuses the internals, etc. But I suspect like when we print an op, we should really print something like init instead of out when it's a tensor, right? Because tensor are immutable. We never do, we actually don't really do destructive update. We create a new tensor, we read a tensor and produce a new one with a partial update of the content in the model. And then we hope that the bufferization, when it's possible, will not create a new buffer and make a copy, but will do the in-place update. But the in-place update relies also on the context, meaning you need to have those, for instance, the flow read-write annotation that you provide, to me means the inter-dispatch region buffer allocation tells you that this value will not be reused. Like it means this dispatch region is the last user of this tensor, so you can, and I don't need the value in it, it's dead. So you can read it, I'm giving it to you as an init value, but you can also reuse it for your output or for whatever you want. or for temporary. But those are optimization annotation. They are not necessarily.
Yeah, they're optimization annotations. I mean,
We
read
could,
and write. I mean, I don't know how to see what the non-optimization case would be. I think the default we started with was read only, write only, and read write was optimization. You could see it the other way too.
In a function, if you have two, I'm getting out of the dispatch region, but in a function, if you have two Linalg generic in a row, both of them gets an init value of 1, for example, right? CSE would be able to give you the same tensor. So now you would have two Linalg generic with reduction that would get the same init tensor value. And now you cannot do it in place anymore because the second one needs the original value. So when you bufferize, you need to preserve, you need a copy. You need to preserve the original init value for the second reduction. If you don't fuse, assuming you don't fuse.
I would say that your initial code to CSE would be doing a wrong thing if there's a reduction and the init value is using the same init value. Oh, okay, you're saying they're two independent reductions. Yeah, you're right. You're right. I see what you're saying. Yeah.
Usually, if there is a reduction, the value will come not from init tensor, but from fill, because you actually initialize it.
Yeah, when I said init tensor, sorry, I meant the initial tensor, not the init tensor value. It would come from a real value. You're right. It would come from something that initialized the init value. And so my point was that this tensor may be reused across multiple Linalg generics. So you don't have a guarantee that the Linalg generic will do an in-place update after bufferization.
Yeah, I think the comprehensive bufferization actually takes care of this case.
Right.
But it's all quite hard.
Yeah, I think maybe the bot point you're making is probably that like it's a assumption that you hope the bufferization will not create a new thing, but the tensor representation has to not rely on it. Right? It's still a correct representation of the program, and then it might be a pessimization to use extra memory, and optimization to use less memory. Right?
Yeah, and so that's why it's not an out tensor; it's really the init tensor. That was my original point.
Yeah, I understand. I think a lot of people are confused by the out. It might be worth changing it. I've had this discussion with a couple of other folks too, and yeah, it makes sense. I guess it's just, you could just use the same. It's maybe you can use a printer trick and parser trick to kind of make it more clear.
Yep.
It used to be inits, that's right, but then we changed it. Yeah. I think Stefan had a question. I thought he unmuted himself, and not sure if he still has a question.
Oh, I was just going to say that it's basically the same problem as register allocation. When you're in SSA form, you have to decide at a certain point how the values get materialized in physical registers, and bufferization has exactly the same problem.
Same thing, exactly.
Yep. Absolutely. All right. If we don't have any other question, we're out of time. We're over time. Thank you, Mahesh. That was awesome to have this end-to-end flow. I think this is really enlightening and helpful for many. Looking forward to what's next. It would be great also to have an update on the runtime side of IREE and how for example, the bufferization across those flow region works and this kind of thing. That looks interesting as well.
Yeah.
At least to me.
Thanks, Maddie. Yeah, not obvious to me that Ben has to give that talk.
Thanks, everyone. Take care. Bye.